Okay, so now we're on to combined loading problems, principal superposition problems, whatever you want to call it. Not sure if you were expecting like an actual lecture for this, but the gist of it would be take all the stuff we've talked about thus far and add it all together. So, you can have situations where there's torque and bending and shear and everything else going on and axial, and you just need to find how that combines together. So let's do this problem here. So we got this sign. It weighs 1,500 pounds, supported by this pipe AB. As well, we got some wind pressure going on the pushing against the face of the sign. It's got so it's uniform wind pressure, 150 pounds per foot squared, and based upon kind of the dimensions given, we want to figure out what the stress of state is at this point here, C, is taken at this cross section right here. This point C, which I'll zoom in a bit more, so you can see that C there is on kind of along the in the Z direction from the center on the inside of the pipe or the tube, whereas D is in the Y direction on the outside of the pipe or tube. So first off, let's kind of figure out what sort of I guess how we can kind of represent this system a bit more simply. So we're going to take that wind force there and figure out what its resultant is. So if we got 150 pounds per foot squared, multiply that by the surface area of the sign, 150 times 12 feet times 6 feet. It's a 12 by 6 sign. So that'll give us a F wind is equal to 10,800 pounds. So that would be there, and then again we've also got the weight of the sign, 1,500. So we're going to want to kind of shift those over so that we can get a more essentially what we're going to want to do is we're going to want to figure out what the net resultant of that is in terms of forces and what sort of moments it's going to cause when taken about A. So simple enough, we'll go back to, well, we know that essentially we know that the force equivalent, like a force moment equivalent, if we take those forces and apply them at A, the forces would stay the same, so it'd still be let's see here, I'm going to call that a Fx is going to be 1,500 pounds, we're going to have an Fy of negative 10,800 pounds. We don't have any forces in the z direction. I'll specify that. And then the kind of the moments that would result. So what we're going to end up here is we're going to have we're going to end up with moments about all axes, because basically the fact that the 10,800 pounds is pushing this direction means that it's causing a moment about the x-axis. So we've got some torsion going on. Also, the fact that it's separated from A by a certain distance means that it's also going to be causing a moment about the z-axis. And then this 1,500 pound force, the fact that it's separated from A by an offset in the z-axis is going to cause a moment about the y-axis. So we can calculate that simply enough by just going back to our going back to our whatchamacallit, going back to statics. Our R cross F is equal to our moment. So the displacement vector needs to be from A to the point where those forces are applied. So I'm going to call, it's not labeled there, the center of that sign is not labeled, but I'm going to call that, let's call that C. Oh wait, no, C's taken. E to F is taken, let's call that G. There we go. So R, A, G, and then the forces acting on G is equal to our moment. So the displacement vector from R, the displacement vector R from A to G, we've got, just got to keep in mind that this is in the center of the sign. So we've got a 3-foot gap between A and the bottom of the sign, and then we got another 3 feet to get to the center of the sign in the x direction. So that'll be again based upon this coordinate system. That'll be x. The positive x direction is down, so that'll be a negative x displacement. So R, AG, that's just going to be equal to negative 6 feet. For the y, there's no back and forth here. Again, it does specify in the question here that we are assuming that it's supported along the outside edge of the pipe. So yeah, it's on that top edge there, I guess. So it's not going to have any y displacement. 0, J, and then our Z, let's see here. So the Z, that'll be 12 feet divided by 2. It does specify here, I guess, that, yeah, 12 feet divided by 2. I'm not going to worry about the possibility of, whether or not the inner radius was included in this 12-foot measurement or not. That seems like a bit niddly and probably won't affect the results too much anyways. So that'll also be 6 feet. And again, our positive Z direction is going here, so that'll be a negative 12 feet as well. So if we're crossing that with our forces, okay, so I -6 feet and 1,500 pounds are J 0 and 0. Wait, no, J 0 and negative are K -6 feet and then 0 force there. And then just I'm going to repeat that. And I'm going to resize this so you can see better. Okay. Okay, so let's see. Going down this way, that's 0. That's 0. Don't need to worry about that. I'll just highlight the ones that we do need to worry about. So we got our J, got our K. Don't have that K. Got this I, and that J is nothing as well. So just the 3 calculations to do. And again, we will get moments about each axis here. The relative moment that force causes at A is going to be equal to, let's start with our I's. So this one's slanting backwards, so throw a minus sign in front there. Both those terms already have minus signs, so two of the minus signs cancel out, leaving a minus sign. So we're at minus 6 feet times 10,800 pounds. Oh, I put feet on there, didn't I? That was stupid of me. Here we go. And I left my units out there too. That's bad. Okay, so anyways, pound feet. There we go. Our J, so it's slanted forward, so it stays as is, and we got a negative sign on the 6. So minus 6 feet times 1,500 pounds, so 9,000 pound feet. And then our K slanted forward, so it stays as is, negative sign, those cancel out, so we're at plus 6 feet times that pound feet. I, J, and K. Okay, so that is essentially what the essentially this is what's going to happen if we take this pipe thing, lop off here, and then just replace what's happening at that cross section with one resultant force moment couple. So we'll end up with these forces being applied, and we'll end up with the with the moments that we talked about. So, I'm just going to redraw that. I'm going to redraw this. Let's look at this. I'm going to redraw it so that we're looking at that cross section with the cross section end on the whatchamacallit, on the left. So based upon the orientation system here, here's our x-axis, and we'll have let's do y in this direction, and then z would be in this direction. So we've got a force in the we're applying on that face a force in the positive x direction. We're also applying on that face a load in the y direction. Sorry, a load in the negative y direction. So that'll be shear. And then we're applying moments. So we got, we're going to be applying one moment that goes about the z-axis. I'm going to have another moment that goes about the x-axis. So that'll be going about that way. And then we got another moment going about the y-axis. Actually, I think I got my directionality. Okay, so I got my directionality right on the z. I think I screwed it up on the x. Yeah, because that's a negative. So what I'm going to do here is I'm just going to go ahead and redraw that direction. So, yeah, so again, based upon our coordinate system, about this direction is a positive, so we got a negative, so it's going in the other direction. And then we've got y. So again, this one's -2. So going this direction would be positive. So instead we've got that. So looking at it that way, we got that. Let's also go ahead and have a look at just the cross section itself. So, what is the size of this? 2 point. Those diameters, right? No, inner radius. So outer diameter 6 inches, and inner diameter 2.75 times 2, 5.5 inches. So if we want to represent these moments, again, here we're looking at this face, kind of going, if we're looking at it this way, that's the x direction. This can be our y direction. This will be our z direction. Then essentially we are going to be having, we can represent our moments as, we got our torque. So our torque, I'm going to use different colors for that. So our torque is about the x-axis, and is a negative moment about the x-axis. So like that. We also got a moment that is about the y-axis. Again, using my right-hand rule to figure out which is positive. So again, this direction would be positive, which means that we have a moment that's kind of gone this way. And then we'll have a moment about the z-axis as well. That one's a positive, so that's going kind of this way, about the z-axis. Right. And we can also kind of add our forces on here. So we've got a shear load. So that shear load is, I'm just going to put that right there. Shear load is straight down. And we've got an axial force. It's compressive. So the 2 points that we were asked to look at, kind of looking at this cross section, again, C and D, zooming in here, like I said, we were looking at just on the inside along the z-axis and just on the outside along the y-axis. So we are trying to look at this spot right here and this spot right here. So that's C was the one around the z-axis, wasn't it? Yeah. So here's C and here's D. So what we're going to need to do is we're going to need to figure out kind of how these loads vary according to position, right? So let's look at C first, and we'll look at each of these forces, each of these moments, and figure out kind of how that affects our how that affects a little cubic element located at that point. So the first one that's fairly easy to look at is our axial force. The 1,500 pounds that is pressing compressive. So axial forces, generally speaking, we can just assume those are distributed evenly. So our stress due to axial, that is going to be equal to negative 1,500 pounds divided by the area. So again, our area here is going to be pi times the outside radius, 3 inches, minus the inside radius. So 2.75 inches squared. We'll be reusing that, so figure out what it actually is. 3 squared minus 2.75 squared times pi. So that A is equal to 4.516 inches squared. So the 1,500 divided by that will give us 2.75 to 332, negative 332 because it's compressive, psi. So that'll be kind of our compressive stress, a compressive stress that basically gets added to the normal stress in the x direction at both points C and D. So there could be other things that affect, well, there are going to be other things that affect our normal stress at those points, but that value needs to be added to both of those when we kind of figure out the total amount. So we got our axial. So what are we worried? So when we're looking at point C here, we're not worried about the stress induced by the moment about the z-axis at all, because point C is at the neutral axis for moments taken about the z-axis. So that's not going to affect our stress at all. So we're not worried about that one. We can ignore that one. We are going to be worried about the moment about the y-axis. So if we're applying, let's look at just that one. So if we're here, we're applying a moment about this axis, to that, then essentially what we're doing is, I just want to double check I got my direction earlier. Yeah. So what we're doing here is we're going to be inducing compressive forces on this side and tensile forces on this side. And otherwise, it's just simple as for the calculations of that, our stress is going to be equal to the moment times moment times our r distance divided by our I, right? We're just back to our flexure formula. So going off that, we need to figure out what our I is. So our I for the circle in general is 1/4 pi r to the 4th. So if we want to calculate the I for this cross-section as a whole, because, tube, I is going to be equal to 1/4 pi times r out to the 4th minus r in to the 4th. So it's 3 inches. That's 2.75 inches. So that gives us That gives us 18.7 inches to the 4th. So plugging in our 9,000 pound-feet for a moment. 9,000 pound-feet times our R here, which is going to be 2.75 inches, divided by 18.7 inches to the 4th. Now obviously we got feet and inches in this one. We don't want that, so times 12 inches per foot. So let's see here. So these inches on top cancel out 2 of these inches on the bottom. The feet cancel out. We're left with pounds per square inch. Good. So 9,000 times 2.75 times 12 divided by 18.7. Okay, so all that together ends up being equal to 15.88 kips. No, not kips, KSI. What am I talking about here? KSI. So, and again, directionality, if we are kind of applying a bending moment this way, then that means that we're going to be compressing over here and we're going to be pulling over here. So that'll be positive. So now from that, we've got enough to kind of start filling out our stress tensor. Because essentially, we've got this tensile, and we've got this compressive. And at that point, those are the only two things that are going to be acting in any of the normal directions. So that's acting in the x direction. So adding those two things together, so essentially the 15,882 minus 332, that gives us positive axial tension aligned with the x-axis of 15.6 KSI. And then when we kind of look back up at what's going on here, again, whatever the other loads that we have, there's nothing else that's pushing in the x direction, and there's nothing that's going to be pulling in the y or z directions either. So this thing isn't being squeezed or pulled apart through the thickness, and it doesn't have any hoop stress at all either. So nothing's trying to cause it to expand outwards or contract inwards. So we know that that's going to be 0 and that's going to be 0. And we'll keep that as KSI. So from there, we can go ahead and try to figure out what our shear stresses are in order to fill out the rest. Let's redraw our diagram here. So that is a force in this direction when we've got, again, x is this way, y is this way, and z's this way. So we've got our transverse shear, 1,800 pounds. So we just need to dig out our transverse shear formula. So that is, our shear is equal to VQ over IT. So V's our shear load, the 10,800. Our Q, we need to calculate that based upon our cross-section dimensions. Our I, we've already got. Our T, that's going to be the total thickness across both of these, basically. So not just the wall thickness, but on both sides. So just correct me if I'm wrong here, but that'll be half an inch. So T is equal to 0.5 inches. That's equal to V. Or I, we calculated already, that was 18.7 inches to the fourth. And then our Q, we just need to kind of base it upon the semicircles, the Q for a semicircle. So again, what we do is we basically find out what the Q would be for this, and find out what the Q would be for the space in between. Take the one, subtract from it the other. So again, Q, and reminder, Q is equal to the area times the y bar value. So if we want to go back to our go back to figuring out what that is. Our A, that's just going to be half the area of a circle. So pi r squared is the area of a circle. So pi over 2r squared. So what do we got here? We'll do it for each little section here. So for the outer portion, our area is going to be 3.14159 divided by 2 times 3 inches to the 3 inches squared. So that gives us 14.14 inches squared. The other one, 3.14159 divided by 2 times 2.75 squared. So this one will be 11.88 inches squared. Call it A1 and actually no, I'll call it AO and AI, outer, inner. And then for the location of the y bar, that is for a hemicircle 4 over 3r over pi. So 4 over 3 divided by pi, it's 0.4244. So times 3 for this one, that gives us 1.273 inches, and times 2.75 for this one, that's 1.167 inches. So yeah, the Q bar, the Q for this object here is going to be 14.14 times 1.273 minus 11.88 times 1.167. And that is 4.136 inches cubed. So now we can solve for what our shear stress is at that point. So we got not 9,000, but 10,800 pounds. And we have that Q we have our I, that's what, 18.7, yeah. 18.7 inches to the fourth. Oh, sorry. Got to the third on our Q here, and then we've got ½ an inch for the thickness. Oh. So down below we've got inches to the fifth. Up top we've got inches to the third. So everything there, once we cancel that out, we're going to have inches squared. So now leaving pounds per square inch is exactly what we expect. PSI. All right. So that gives us 4.78 KSI. So orientation-wise, if we're applying the a shear force to this face here, downwards, that means that this shear force will be on the negative x face. So like if I'm drawing a little cube here, if I make it x, y, z, you gotta keep in mind that like the pipe's going into the page that way. So this is on the negative x face. So that's essentially this. So I'm applying it on the negative x face in the negative y direction. So x, y, z. Oh, sorry, I realized that's a bit under my face here. So I'm applying it here. So essentially, counteracting that, we need to have it on the positive x face in the positive y direction. So that'd be a positive shear there. And then obviously we get the corresponding yx shear as well. So I'm going to trans and in brackets xy. And now we got the torque. So we draw a cross section here. That is terrible. Better. So we're applying a torque as well. So we're applying a torque about the x-axis around this way. So like this. So that's going to be applying a force on, again, that'll end up being on the negative x face, and it'll be applied in the positive x direction. So when we apply that to the negative, to the positive y face, negative x direction. So this shear is going to start to cancel out this shear here. As opposed to what's going on over here. Basically, it's the opposite. They're going to combine together on the other side, but we're not doing that portion of the question. So, anyways, as for what its magnitude is, we just need to go to our torsion formula. Okay, so our torsion formula is that our shear is equal to the torque times the radius divided by j. What's j? Again, j is equal to ix plus iy. Actually, let me think here. Given this coordinate system, that'd actually be iz and iy. It's equal to j. But again, they're both circles. They're both circles. They're both oriented. Just looking at a circle from slightly different orientation doesn't change the eye at all. So in this case, our I is just going to be 2 times, sorry, our J is just going to be 2 times I. So our calculation for I was, so 2 times 18.7 inches to the fourth. So that's going to be 37.4 inches to the fourth. Our torque, what was our torque there? Magnitude of our torque is 64,800 pound-feet. And if we want to convert that to pound-inches, multiply that by 12. So our shear stress as a result of that is going to be inches times 2.75 inches, that's our radius, divided by 37.4 inches to the fourth. So that is 57.18 KSI. So again, like I said, that we look at a cubic element based on a coordinate system, that's being applied in the positive y direction on the negative x face. So on the positive x face, in order to counterbalance that, that's going downwards. So that cancels out from what we've got going on here. Essentially our stress in the xy is going to be equal to negative 57.18 KSI plus the 4.78 KSI. That will give us negative 52.4 KSI. So if we head back up to here, that will be our XY shear stress, negative 52.4 KSI. And then again, you will recall that if we have negative shear stress like this on the x face in the negative y direction, in order for this to be balanced, we also need to have a corresponding shear stress on the y face in the negative x direction. So this matches this here. And then kind of going back up to our loading situation, there's nothing that's going to be causing any shear stress in there's nothing that's going to be causing any shear stress at all in any of the z-axes here. So not in your yz or not in your zx. So we can just go ahead and fill in the rest of that as zeros. And that is the stress state at that little, at that bit there. So we'll have a look at what's happening with at D next. So I'm just going to go ahead and copy and paste this section here, so we can kind of, because everything's still applicable there, we're just looking at a different point. So previously we were looking at C over here. We're not worried about what's going on at C. Nope. So I'm gonna try to erase just the stuff there. There we go. Instead, we're worried about what's happening up at D. So again, the axial stress is applied equally across the entire thing. So the fact that we're compressing in the x direction still means that the axial stress is going to be negative 300 and what was it? Negative 332 psi. That hasn't changed at all from location. Everything else does change from location, however. So let's just go ahead and having a look at this. The shear load there didn't copy over. That having been said, I'm going to just go ahead and erase the stuff that doesn't really count here. So you will recall that the way the shear distribution works is you get some sort of maximum in the middle and you get 0 at the top and the bottom when you're applying a vertical load. So, you know, shear distribution on this probably looks something like this. So at D, which is at the very outside, we're looking at the part on the outside, not on the part of the inside edge here. So at the very outside, we know that the transverse shear caused by this vertical load is going to be 0. So let's just erase that. We're not worried about that right now. We also know that if we're taking, if we're taking, here's the z-axis, here's the y-axis. Again, x-axis is this way. If we're taking a moment about the y-axis, then the stress caused by that's going to be 0. So I'm going to just go ahead and erase the moment about the y-axis as well. So that was this 9,000 pound-feet here. We are, however, worried about what's going on with the moment about the z-axis. So again, that's that moment right there, this 64,800 pound feet. So that's still of concern. The moment about the x-axis as well, it still causes torque. The magnitude of that torque, the magnitude of that torque again is proportional to its proportional to the radius. So let's deal with the bending stress first. We'll deal with the bending stress first. So again, our bending formula is equal to m r over I. So as we increase, as we get to the outside edge here, that's 3 inches. 3 inches from center to outside. And our I is still the 18.7 inches to the 4th that we'd calculated earlier. Again, we'd calculated that about a different axis, but it's a tube, so they're the same kind of about any axis in the YZ plane. So stress we're causing there times, so we got our moment, we got our distance from the neutral axis, we've got our 18.7 inches to the 4th, and we got feet and inches here again, so let's go ahead and convert that. So 12 inches per foot. Feet cancel out. All but 2 of those inches cancel out. We're left with PSI here. So 64800 times 3 times 12 divided by 18.7. So that gives us a pretty large number. So that's going to be 124.7. I was going to two decimal places previously, so stick with that. KSI. And again, if we are applying a moment to this face, if we're applying this moment, then that means we're going to be compressing this portion here, and we're going to be stretching this portion here. So that'll be at D there, it's going to be positive. So I'll just put a plus sign there. So again, that's all we're worried about for axial, right? That and the, for normal stresses. So that's, again, still in the x direction. So we've got 124.75 minus the 332 psi. So 124.42 KSI. And again, the x direction is the only one that's going to have any normal force on it. There's nothing squeezing the tube from either side. It's not getting thinner like that. It's there's no force causing it to get thinner. It will be getting thinner due to Poisson's ratio, but we're not calculating that, so let's not worry about this. It's also not going to be, what am I trying to say here? It's also not going to, it doesn't have any hoop stress, either positive or negative. Nothing's trying to stretch it out like that. So our y direction is 0, and our z direction is 0. I would note that since we're using x, y, and z for this coordinate system, if there was hoop stress, in this coordinate system at D, the hoop stress we calculated would be z along the z-axis. Whereas in the previous step, if there had been hoop stress in that, at point C, that would have been in the y-axis. Because again, we're at a different point on the circle, so the orientation is different. So we can fill this out right now, KSI. And then now we just need to figure out what our shear stresses are. So again, we got the one bending moment that's about an axis that'll cause it to cause stress to rise there, but the axial. The other bending, there's two other bending moments. There's one about the y-axis, which because D is on the neutral axis there, that doesn't cause any stress. And then we got the x-axis one. So the x-axis one is the one that's going to be causing some torque. So again, just go back to our torque formula. The shear due to torque is equal to the torque times the radius divided by our j. So I'm sure you'll recall that the so the value of that torque is 64,800 pound-feet. That is a terrible 4. And again, times 12 inches per foot. The radius there, 3 inches. And then our J, again, that's twice our I. So 18.7 times 2, which was 37.4 inches to the 4th. So again, these 2 inches on the top cancel out, all but 2 of the inches on the bottom, and we're left with pounds per square inch, which is what we expect. So numbers. So that means that at that point we're getting a torque stress due to shear stress due to torque of 26.37 KSI. So just kind of looking at that diagram again, the torque is being applied about the it's in the negative direction, and it's being applied about the x-axis. So it's going, well, I'll use a different color for that. Let's use green for that. So it's being applied here like this on this face. So at a little cube that we're looking at here, wait, no, not there, on the outside. At a little cube that we're looking at here, we kind of redraw this in this coordinate system that we're probably a bit more used to looking at, x, y, z. Then that force would be on the negative x face, and it would be applied in the negative z direction. So that one's going like this here, and therefore it's going like this here. So on the negative x face, it's going in the negative z direction. So that means on the positive x face, it's going in the positive x direction. And then again, likewise, in order to remain in equilibrium, we've got to have we've also need to have the corresponding shear stress on the zx. So we got xz and we got zx. Both of those are positive, and both of those are 62.37 KSI. So xz and zx. And that's it, because again, we're at the very top, so that transverse shear that developed at the other part due to the shear load, it's not there at all. So we're not worried about that. So we don't have any y's. We don't have xy, and we don't have zy either. So that is the stress state at point D. And yeah, I think that's all the question asked for. Let me just double check. Show the results on a differential volume element located at each of these points. Neglect the second. Yep, that's all we need. So there you go.